So some examples I want to go through. There are a total of 3 examples. I want to go through an algebraic example. I want to go through a tabular example and a graphical example of dealing with some motion problems. So here we have an explosion that propels a rock straight up with an initial velocity of 160 feet per second. It reaches a height of s of t equals 160t minus 16t squared feet after t seconds. So a lot of times a little picture can help. So we have a rock, there's an explosion, it's going up, and it's coming back down. We want to know how high the rock goes. So in my head, what I'm picturing is, okay, what can I say about the rock? Well, I know it has an initial velocity, of 160 feet per second. So that's the velocity when time is 0. And as it starts going up, it's actually slowing down until it reaches the very top here. At the top point here, my velocity should equal 0. So what I need then is, okay, if I can figure out at what time is the velocity 0, I can plug that time into s of t to figure out the height. So to do that, I need the velocity. Well, the velocity is the derivative of displacement. That would be 160 minus 32t. And then I want to set that equal to 0 because my rock has to stop before it turns around and comes down. And solving this, almost forgot my negative signs there, I get that t is 5. That doesn't answer my question of how high does it go. That's the time that it's at its highest point. So I need to plug that in for t in my s of t. So s of 5 is going to be 160 times 5 minus 16 times 5 squared, which is 25. So that is 800 minus 400, which is 400, and s of t is measured in feet. And there is how high the rock goes. Now, could I have figured out that because it's quadratic, where there's the vertex? Yes, but personally, especially now that we know the shortcuts for the power rules, and it's so easy to find v of t now, I find this to be a little bit easier. Okay. Then we're asked, what are the velocity and speed of the rock when it's 256 feet high on the way up and on the way down? So we said it goes 400 feet, so that means that there is a time where our rock has a height of 256 feet. So I need to know at what time does the rock have to hit 256 feet. So I set s of t equal to that, 256 feet. I'm going to move everything to the right-hand side just so I have positive t squareds. I'm going to divide everything on both sides of the equation by 16. And then I can solve this by factoring. I get t equals 2 and t equals 8. And this should make sense because there's a time when the rock is going up, t equals 2, and then the time when the rock is coming down, t equals 8. So it makes sense that there are 2 times. But we want to know the velocity and speed going up and down. So I need the velocity and speed when t is 2, and I need the velocity and speed when t is 8. Fortunately, we already found the velocity equation. So on the way up, I just plug 2 into my velocity equation. So v of 2 is equal to 160 minus 32 times 2. Well, 32 times 2 is 64, so this is 96 feet per second. Oops, apologies. Well, my speed is the absolute value of that. Well, that's already positive, so my speed is also 96 feet per second. When t is 8, same idea, so v of 8 It's 160 minus 32 times 8. 32 times 8 is 256. Minus 160 is negative 96 feet per second. The speed is the absolute value of that. So my speed is going to be a positive 96 feet per second. And there are my answers for that. The algebraic do tend to take the most time to go through. Tabular ones, a bit different here, because there's really kind of two things that we could be asked. One is to find an average velocity. So please note now, we have a table of times with displacements of whatever it is that's moving. And we're being asked to find what is the average velocity from 0 to 14. Well, this is the change in, is my displacement here. So I'm doing the change in displacement over the change in time. And I don't need to simplify. But if they ask me for units, my numerator is in meters, my denominator is in seconds, and there is our average velocity. They could also ask us, hey, we want you to estimate the velocity at t equals 5. Now, please note, they don't tell me what kind of velocity, so we assume it is the instantaneous velocity. So the idea of this is I want to get as close to 5 when I find the slope between 2 points as I possibly can. I could technically use 0 and 14, but that's not going to give me the best estimate. I want to get the best estimate I can, so I need to move closer. So not 0 and 14. I could use 4 and 10. But again, I could get closer. I could use 4 and 9, but I can still move closer. I could use 4 and 6. And at this point, this is basically the symmetric difference quotient that the calculator would be using, just with a larger h. But I can actually get closer to the 5. And I'm going to have two options here. I could use 4 and 5, or I could use 5 and 6. They don't tell me whether I should be approaching from the left or the right, so it's my choice, which means either would be counted as correct. I would only need one of them. Because if you remember, when we find the slope at a point, we always use the point of tangency as one of the 2 points. So since I'm told to estimate the velocity at 5, I should use the t equals 5 as one of my 2 points. The other one should be as close to the 5 as I can get. And I just happen to have 2 choices for the other one. So if I go with the 5 and 6, in other words, from the right, I would have my slope with the change in y's over the change in x's. And again, top is in meters, bottom is in seconds. So this is one that I could use, which, if you are compelled to simplify, would be 6 meters per second. Or if I prefer to use 4 and 5 and approach from the left, I'd have 18 minus 12 over 5 minus 4. Top is in meters, bottom is in seconds. That is also 6 meters per second. So if you notice, it didn't matter which of these I used, as long as I was using the 5, our point of tangency, and one other point. Now, if they had not included 5 in my table, like say they had said, let's estimate the velocity when t equals 7, well, then I would use, like the symmetric difference quotient, if I had to find for t equals 7, I would use 6 and 9, because those are as close to the 7 as I can get. So then, graphically, I have a graph of displacement. I'm being asked to graph velocity and speed. Well, remember that since velocity is the derivative of displacement, that means that velocity is the slope of displacement. So if I think of this then as I'm graphing slope values. So I'm going to, on my graph of my displacement, just to figure out all my slopes. So this has a slope of 2, this is a slope of 0, -1, 0, +2, and -4. So now for my velocity, from x equals 0 to x equals 1, I have a slope values of all 2 there. From x values of 1 to 2, I have slope values of 0. I should say these are my velocities. From 2 to 3, I have slope values of -1. From 3 to 4, I have slope values of 0. From 4 to 5, slope values of +2. And from 5 to 6, slope values of -4. Now, at x equal 1, 2, 3, 4, 5, I can see in my graph I have corners, which means that the slope does not exist at the corners. So I need to have open dots at each jump. The endpoints are kind of a personal choice. I typically will put closed dots at the endpoints because we do have one-sided derivatives. And if I tried to approach from the other side, I'm actually outside the domain, and that doesn't count. Then for speed, speed is the absolute value of velocity. So all I really have to do is just graph the absolute values of these slopes. So for speed, well, from x of 0 to x of 1, the speed is the same as velocity. So from 1 to 2, still the same. From 2 to 3, makes it +1 for the speed. 3 to 4, speed is the same as velocity. From 4 to 5, speed is the same as velocity. But then from 5 to 6, I need to make that positive, so speed would be a +4. One way to think about it is we're just taking anything that's below the x-axis and reflecting it over into the first quadrant.